Momentum and rotation review 1. For the perfectly inelastic collision shown, find all of these quantities. Perfectly inelastic collision means that the objects stick together. We want to find the final velocity of the two-mass system. In this collision, momentum is going to be conserved. So what's the initial momentum? It's very important whenever we're talking about momentum, especially if the two objects are going in different directions, we have to assign a direction to be positive. And if it's not that direction, then it's negative because momentum is a vector. So I'm going to choose to the right to be positive. So the initial momentum is going to be mass times velocity of that object plus mass times velocity of that object. This velocity is -3 because it's going to the left. That needs to equal the total momentum at the end. At the end, we're told that these masses are stuck together, so the total mass will be 8. And what's V final? 25 minus 9 is equal to 8 times VF. So I'm thinking that VF comes out to be +2. In other words, 2 meters per second to the right. What's the impulse of the 5 kilogram mass on the 3 kilogram mass? The impulse is equal to the change in momentum. That's one thing it's equal to. What would be the change in momentum of the 3 kilogram mass? The change in momentum would be the mass V final of the 3 kilogram mass minus V initial of the 3 kilogram mass. Let's figure that out. 3 kilograms. V final is 2 minus, what's V initial for the 3 kilogram mass? V initial was -3. Those end up creating a +3 in essence, don't they? And that gives us +15. The units for impulse are the same as the units for momentum. One such unit is kilogram meters per second. And that's positive, which means it's directed to the right. What about the impulse of the 3 kilogram mass on the 5 kilogram mass? Again, the impulse is equal to the change in momentum. So how does the momentum of the 5 kilogram mass change? It's 5, its mass, times V final, which we said was 2, minus V initial. And its V initial was a +5 here. So that comes out to be -15 kilogram meters per second. That shouldn't surprise us. The impulse that one mass imparts to the other is numerically equal to, but opposite in direction of the impulse of the other on the one. Part 4, if the time of impact before a common velocity is reached is 0.5 seconds, find the average force the 5 kilogram mass exerts on the 3 kilogram mass over that time. So we said here on the left side of the screen that the impulse is equal to the change in momentum. The other thing that the impulse is equal to is, in essence, the force times the time. Now, if the force is constant, or if we want to find the average force, in which case we're assuming it's constant, then this right side just turns into F times time, which means the F is what we're looking for multiplied by time, and that's the impulse. The force on the 3 kilogram mass is going to be the impulse on the 3 kilogram mass, which is +15, and the time is half a second, so the average force is +30 newtons. And real quickly, shouldn't the force on the 3 kilogram mass be in the positive direction? Let's go back to our picture here in the upper right corner now. Isn't it true that this 3 kilogram mass is going to experience a force in the positive direction when it gets bonked by this 5 kilogram mass? And lastly, we don't even have to show any work for this last one. What's the average force that the 3 kilogram mass exerts on the 5 kilogram mass? This is a Newton's third law thing, isn't it? Action, reaction. The 3 kilogram force will exert an equal but opposite force on the 5 kilogram mass. And one more time, let's look at the picture on the top. Doesn't the 5 kilogram mass feel a force directed to the left? Because it's going to slow down, you see, from 5 meters per second to 2.